Thank you for tuning in for my presentation. This presentation is all about the mean waiting time in large-scale and critically loaded power of D load balancing systems. This means that we are considering load balancing policies which distribute jobs over a large number of servers. Moreover, we assume that the arrival rate is such that the system is close to instability. Our main focus in this presentation is on workload-dependent load balancing policies. At the end of this presentation, we discuss how these results may also be applied to queue-length dependent load balancing policies. As we are considering load balancing policies which balance the load based on the workload present at the queues, we represent queues by the amount of work that they currently have. This is a continuous amount, and we can represent the queues as glasses of water which are leaking at the bottom at a constant rate equal to 1. A job is then represented by a bottle of water which needs to be emptied in one of these glasses. In the simplest case, we simply empty this complete bottle of water into the glass with the least amount of water. Let us formalize this setting a bit. We assume that we have an arrival rate equal to lambda times n, with n the number of servers, or in this case, the number of glasses of water, and job sizes which are exponential with mean 1. We have our n glasses of water, and the bottle arrives. To convey this message as clearly as possible, we simply consider the least loaded D, or in short, the LLD policy with D equal to 2. For this policy, the dispatcher selects 2 glasses and we assign the bottle to the glass with the least amount of work at the time the bottle arrives. We empty the complete bottle into the glass, and afterwards we no longer need to distinguish between the work from this job or the work from the jobs which were already present, and we are ready for the next arrival. From this, it is not hard to see that the workload distribution for the LLD policy is independent of the scheduling policy used to finish jobs. However, the waiting and response time distribution do depend on the used scheduling policy in a non-trivial way. In this presentation, I will always assume that the used scheduling policy is first come, first served whenever we talk about waiting times. As we are interested in the waiting time for a critically loaded system, we should use very large glasses. As the mean job size is equal to 1, we find that the system becomes unstable when lambda gets close to 1. Therefore, when we set lambda equal to 0.8, the system is still far from being unstable, and we find that the workload at the queues remains fairly small most of the time. In fact, we have some interval such that the workload of almost all queues lies in this interval. As we increase the value of lambda to a value close to 1, we find that the loads on the queues also increases. But we observe that all queues still have a similar workload in the sense that we can simply move our interval up, and the workloads at almost all of our queues is still contained in this interval. You may be doubtful of this, as I am making my point using drawings which I made and which may not be based on anything but my gut feeling. But fear not, we have done numerical and analytical work to back up these claims. Here we plot the complemented cumulative distribution function in W. That is, the probability that the workload exceeds the value W as a function of W. We made these curves for a variety of values for lambda, which are very close to 1. In this plot, you should look at the place where the curve decreases, as this is the place where almost all workloads of the queues are contained. We can again draw a box with a bounded width which contains almost all queues for our system. We observe that as we increase the value of lambda closer and closer to 1, we do not need to enlarge our box, but we simply need to move it slightly to the right to make it contain all queues for this larger arrival rate. Even for an arrival rate as large as lambda equal to 1 minus 10 to the power minus 16, we can still clearly see that the same bounding box as for lambda equal to 0.99 can be used to contain the workload of almost all queues. Using this observation, we can define some value w which depends on the arrival rate lambda and also on some small value epsilon which you do not really care about in this presentation. This value w epsilon lambda is chosen right before the point at which the curve shown in this plot starts to fall off. Therefore, if one were to compute the area under these curves for a very high value of lambda, the difference between letting this integral run up to infinity or letting it run up to this value of w epsilon lambda is just some finite constant. As the area under the curve clearly diverges to infinity as we let lambda increase to 1, we may ignore this last part of the integral. For this integral from 0 to w epsilon lambda, we can see from our plot that f bar is very close to 1. Therefore, this integral may simply be approximated by the constant value w epsilon lambda, which increases to infinity as lambda approaches 1. If we assume that the scheduling policy is first come, first serve, we can show that this integral, which represents the mean workload, also closely approximates the mean waiting time. This way, we were able to obtain a very simple formula for the mean waiting time for LLD when the system load increases to 1. Okay, so we know that the expected waiting time can be approximated by w epsilon lambda. We are interested in computing the limiting value of the expected waiting time as the load approaches 1. Of course, this limit is easy to compute. It simply diverges to infinity, right? Well, to overcome this issue, we need to scale down by another function that increases to infinity. To this end, we use the same denominator as the one which was used by Mitsemacher when he computed the limiting response time for the SQD policy, namely the logarithm of 1 minus lambda. As a side note, I would like to point out that Mitsemacher has shown a similar result to what we are going to show now for the SQD policy. However, Mitsemacher's proof is quite technical and heavily depends on the closed form solution which is available for the SQD policy, while our proof is based on an ID which can be applied to a wide variety of load balancing policies. Therefore, we will not go further into depth on the proof of Mitsemacher, but we would like to note that he was the first to consider the limiting value which is the subject of this presentation, but he only considered the SQD policy. With that aside, let us continue with our analysis. As we have already shown, we find that this limit reduces to the limit with the value w epsilon lambda as the nominator, and we are able to show that this limit converges to the very simple expression 1 over d minus 1. The fact that we are able to use this denominator to obtain a finite non-zero value shows that we have an exponential improvement over random routing. This may also be seen from our limiting result, as random routing corresponds to taking d equal to 1, and we see that the limiting value we find diverges to infinity as d approaches 1. We have gone to one extreme, sending lambda to 1. On the other hand, we might just as well send lambda to 0. It is not hard to see that if we take the same expression and we send lambda to 0, we obtain 0 as the limiting value. This doesn't really tell us anything, except that the waiting time is close to 0 for small values of lambda, which is obviously true. We observe in these plots that the quotient we have been considering starts in 0 and has a steep ascent as lambda approaches 1. If we are able to make these graphs more flat, We will also be able to find better approximations of the expected waiting times for high and low arrival rates. To this end, we define p lambda as the probability that a random job is routed to an idle server for the LLD policy. We find that if we use the log of p lambda in the denominator, the limiting value for lambda to 1 remains unchanged, while the limit for lambda to 0 becomes 1 over d, which is simply some finite value. Also, if we redo the plots, we observe that the curves are much more flat, and especially as d increases, the limiting values can be used as good approximations. We also observe that the curves increase monotonically. We are able to analytically show this for the LLD policy, and this in turn shows that we can use the limiting values not only as approximations, but we can use them as bounds on the expected waiting time. These bounds become highly accurate as d increases. We now consider a second model, the LLDK model, where we set d equal to 3 and k equal to 2. As for the LLD policy, setting d equal to 3 indicates that we consider 3 arbitrarily selected queues in order to distribute the incoming jobs. K equals 2 means that we consider batch arrivals with batch size equal to 2. Therefore, 2 jobs arrive at the same time. We then assign these 2 jobs to the 2 least loaded queues amongst the 3 queues which were selected, and we completely empty these bottles into the chosen glasses. For this policy, we can again compute the value p lambda, which signifies the probability that a bottle is emptied into an empty glass of water. While the expression might look a bit more complex, it is still a very simple closed form expression. We can again compute both the limit for lambda tending to 1 and 0 for the mean waiting time, and we obtain similarly simple expressions for this load balancing policy. Let us now discuss the general framework which we have developed. In general, we have found that the probability that the workload at the cavity queue exceeds W can be found from a simple ordinary differential equation, where the function t lambda depends on the used policy. This is the case for many workload-dependent load balancing policies, and our proof for the limiting results we have shown is completely based on the definition of this t lambda function. For example, if you consider the LLD policy, this t lambda of u is defined as lambda times u to the power d. Associated to this t lambda function, we define some additional variables. We have u lambda, which is a fixed point of t lambda, chosen as the smallest fixed point which exceeds 1. We then define a function h lambda, which is based on t lambda and u lambda. From these definitions, we then compute the 2 constants, namely capital A and capital B. Here, lowercase b is some problem-specific constant which is simply equal to 0 for most models we have considered. We then require some additional technical assumptions, and from this we can compute the limiting value for lambda approaching 1. Computing these a and b values is generally quite easy. Therefore, we can easily conjecture a limiting value. However, proving these additional assumptions might prove to be challenging for certain models. For the case of lambda close to 0, one does not need to go through these steps, but all you really need to do is make a simple problem-specific proof. We have found that if you consider queue-length dependent load balancing policies like SQD rather than LLD or SQDK rather than LLDK, you can obtain very similar results. If we denote by UK the probability that the cavity queue has k or more jobs, we find that UK plus 1 equals t lambda of UK, where t lambda is the same function for the queue length and workload dependent variant of a certain policy. For example, for the SQD policy, we again set t lambda of u equal to lambda times u to the power d. We then compute the same value of u lambda, a and b, and with pretty much the same additional assumptions, we obtain a similar limiting result. This means that if you complete the proof for a workload dependent load balancing policy, you get the high load limiting result for the queue length dependent load balancing method for free. One thing that is very nice about this subject is that there is still a lot of future work possible. For example, policies we have considered will always assign only one job at a time per queue. You might want to generalize this to assigning multiple jobs to a single queue at one arrival. Also, we have assumed that job sizes are exponential. You may want to generalize this to general job size distributions. Also, we have seen for the LLD policy that the quotient we consider is monotonic in lambda, but we have not proven this analytically for other load balancing policies. Maybe it's also possible to prove it for other load balancing policies, because from numerical experiments we have found that this monotonicity in lambda still holds true. And there are many more directions in which this research can be extended. With that said, I would like to thank you for the time you have taken to watch this presentation, and I hope to have inspired you to start working on these open problems.